The science behind ion propulsion. Introduction. Hey everyone! Welcome back to CHIZHIM Science Tech, where we decode the universe one breakthrough at a time. Have you ever wondered how spacecraft travel vast distances without using traditional rocket fuel? What if we told you that some of the most advanced space missions are powered not by combustion, but by electricity? Today, we're diving into the science behind ion propulsion, a revolutionary technology reshaping the future of interstellar travel. From physics to engineering and from sci-fi dreams to real-world spacecraft, this video will take you deep into the core of how ion engines work, why they are efficient, and how they're transforming our journey into the cosmos. Chapter 1. What is ion propulsion? Ion propulsion is a method of spacecraft propulsion that uses electric fields to accelerate ions, charged particles, to incredibly high speeds, creating thrust. Unlike traditional rockets, which rely on explosions of chemical fuel, ion propulsion works by ejecting ions at extremely high velocities, sometimes up to 90,000 meters per second. Here's how it works in simple terms. An atom, usually xenon, is ionized, given an electric charge. The ions are then accelerated through a grid of electrodes using electricity. As these ions shoot out of the back of the spacecraft, Newton's third law kicks in. For every action, there's an equal and opposite reaction, producing forward thrust. While the thrust is tiny, less than the weight of a sheet of paper, it's continuous, and over time, it allows spacecraft to reach enormous speeds with minimal fuel. Chapter 2. The physics behind it. Ion propulsion is grounded in electromagnetism and classical mechanics. 1. Ionization process. Electrons are stripped from xenon atoms using high-voltage electricity. This creates positively charged xenon ions. 2. Acceleration. These ions are directed into an electric field between two grids, a positively charged one and a negatively charged one. The ions are repelled by the positive grid and attracted to the negative one, gaining immense speed as they exit. 3. Electron neutralization. A cathode sprays electrons into the ion stream after they exit to neutralize the charge, preventing spacecraft from building up a net positive charge. The result? A gentle but persistent force that, given time, can push a spacecraft faster than any chemical rocket ever could. Chapter 3. How ion engines differ from chemical rockets. Feature chemical rockets' ion propulsion. Thrust very high, very low. Fuel efficiency, ISP, low, 300 to 450 seconds, very high, 3000 plus sec. Fuel type liquid or solid prop inert gases like xenon. Usage duration short bursts continuous for months, years. Ion propulsion is 10x more efficient than chemical propulsion in terms of fuel usage. That's why NASA uses it for missions requiring long-duration, low-thrust maneuvering, like the Dawn mission to Vesta and Ceres. Chapter 4. Real-world applications. NASA's Deep Space 1, 1998. First to use ion propulsion in deep space. It demonstrated the viability of the technology for future missions. Dawn mission, 2007. Explored Vesta and Ceres, two of the largest objects in the asteroid belt. Ion propulsion allowed it to orbit and leave multiple celestial bodies, a feat chemical propulsion couldn't achieve. ESA's BepiColombo, 2018. Currently en route to Mercury. It uses 4 ion thrusters to perform multiple flybys and gravity assists. These missions prove ion propulsion is not theoretical, it's being used right now to explore our solar system. Chapter 5. The power source, where the energy comes from. Ion propulsion requires a lot of electricity, but not in the explosive way chemical rockets do. Most ion engines get their power from solar arrays, converting sunlight into electrical energy. For near-Earth or inner solar system missions, solar power is sufficient. For deeper missions, like to Jupiter or beyond, radioisotope thermoelectric generators, RTGs, or future nuclear power sources may be used. A spacecraft like Dawn used 10 kilowatt solar panels, massive arrays that unfold in space, to power its ion thrusters continuously over many years. Chapter 6. Advantages of ion propulsion. Fuel efficiency, 90% less fuel than traditional systems. Long-duration thrust, can thrust continuously for years. Multiple destinations, flexible enough to change orbits or flybys mid-mission. Reduced mass, smaller fuel requirements equals lighter spacecraft equals cheaper launches. These advantages make ion propulsion ideal for robotic missions, asteroid exploration, and eventual interstellar probes. Chapter 7. Challenges and limitations. Despite its promise, ion propulsion has several challenges. Low thrust, not suitable for lifting payloads from Earth, can only work in space. High power requirements, demands more electrical energy than current small satellites can generate. Slow acceleration, needs weeks to months to build up useful velocity. Technology complexity, systems are intricate and sensitive to damage or failure. That's why current missions often combine ion engines with other systems, or use them after reaching orbit. Chapter 8. Future developments. NASA's next engine. Next-gen ion thruster producing even higher thrust and efficiency. VASIMR, Variable Specific Impulse Magnetoplasma Rocket. Uses plasma and magnetic fields to produce even more adaptable thrust for future Mars missions. AI plus ion drives. Future missions will integrate ion engines with AI-based navigation systems for autonomous deep space travel. We are also looking at nuclear electric propulsion, which could power ion drives for missions to Mars or even the outer solar system. Chapter 9. Could we use ion propulsion for human spaceflight? Ion propulsion is currently used for robotic spacecraft, but future crewed missions could benefit too. Challenges. Ion drives are too slow to leave Earth or carry large human habitats. Chemical boosters are still needed to lift off. But once in space, ion propulsion could sustain human missions by reducing fuel mass and allowing orbital flexibility. NASA's Artemis support missions, Lunar Gateway, and potential Mars cargo transport may eventually employ hybrid systems using ion engines. Chapter 10. Ion propulsion and the search for alien worlds. Ion propulsion could be our ticket to reaching other star systems, not in weeks, but over decades. Think of missions like Breakthrough Starshot, using light sails and possibly ion drives to reach Alpha Centauri. Interstellar probes, powered by nuclear electric ion engines to travel beyond the heliosphere. The goal? To explore alien worlds that may host life, water, or even civilizations. Call to action. Host on camera. Ion propulsion is more than just a cool sci-fi concept. It's a real, working technology driving us deeper into the universe than ever before. From visiting asteroids to one day reaching exoplanets, the possibilities are limitless. Thanks for joining CHIZHIM Science Tech on this electrifying journey through the science behind ion propulsion. If you enjoyed the video, don't forget to like, subscribe, and hit that notification bell so you don't miss our next deep dive into the future of science and technology. Stay curious, stay inspired. This is CHIZHIM Science Tech, signing off.